Yes, Austin. I cannot do physics homework for you, but I did win the physics award when I was in high school, so if that helps. The midpoint sum is different. I'm not going to evaluate the height at 1, and I'm not going to evaluate the height at 2. Where do you think I'm going to evaluate the height? 1.5. So that's where the height is evaluated. Then as you can see, as I draw the rectangle, it will span over to both 1 and 2. So I have a little bit of an overestimation, and I have a little bit of an underestimation. So this is generally better than a right hand or a left hand. Same thing between 2 and 3, I'll evaluate the height at 2.5. Again, that will give me, in this situation, a little bit of an over and a little bit of an under estimation. Now, the part that I'd like to focus on for you, that's, so again, we evaluate x is equal to 1.5 and x is equal to 2.5. I think that this is the most important piece for you to learn today, that the x values for we evaluate the heights change, and try to understand why they are what they are. So, well, and we'll, so right here, we will do the right hand, left hand, midpoint, and trapezoidal sum given a table. We'll do one given a graph. We'll do one given an equation. So, and then the last one right here, trapezoidal sum. This is my favorite. And I'm going to draw the right-hand sum in blue. And then I'm going to draw the left-hand sum in red. If I were to average the right hand and the left hand, if you look at these two rectangles right here, do you agree that the blue rectangle shares all of the red rectangle? So therefore, if I were to average the two, I would take the amount that's left over and I would just split it in half, correct? And when I do that, I get this green shape, which is a trapezoid, isn't it? It's standing on its end. If we were to tilt it to the side, you would see that the trapezoid looks like that, where this is base 1, this is base 2, and then this is my height. And you can find that area. But we don't have to go through all the work of actually using the equation for a trapezoid in order to find the trapezoidal sum. What we simply do is use this geometric argument, which is that we take the average of the right hand and the left hand. So how do we find trapezoidal sum? We don't evaluate at certain x values necessarily so much as taking the right-hand sum plus the left-hand sum and divide it by 2. So the notes will take us pretty much the hour, but the first few we could get through pretty quickly if you really focus. This is a type of problem we've seen that's very similar before, but this time we're going to lay it out a little bit differently with our different types of sums. Use the following table to determine the approximate area bounded beneath the function over the interval -2 to 6. So the first thing that we do is we determine the width of the interval. 8. So this says we want the right-hand sum of 4 rectangles, so 4 subintervals. So therefore, the width of each rectangle would be 2. Now, please note this piece. If this is B and this is A, and N is the number of rectangles, then the width of the rectangle will be B minus A divided by N. The end point minus the beginning point divided by the number of rectangles, right? Okay, so the right-hand sum of 4, we already said that it's going to be a width of 2. So therefore, I have to draw widths of 2. So those are my widths of 2. This is my first sub-interval. I want to evaluate the right-hand side of it. The right-hand side would be evaluated at 0, and I would get 1. Then, yep, at 2 I get 7. At 4 I get 8. Good. Is that clear to everybody? So I get 8 plus 8 is 16, 22, so 44. What's going to change for the left-hand sum? Yeah, exactly. So this subinterval, you're going to start at 5. Or at an x value of -2, which will give you 5. And then you still have the 1, you still have the 7, you still have the 8, but you leave off the 6. So 6 plus 7 is 13, 21, so 42. Here's a mistake that a lot of people make right now. When they go to the midpoint, for some reason they change the width. The width of the rectangle stays the same. Why? What would you change it to? This is what I can never figure out. 1.5? Okay. Thank you for sharing. I just don't see it. But anyway, so what's the middle of this interval? Yeah, -1 evaluated 10. Very good. Then? Good. And so I get 10 plus 10 is 20. 16 will be 36 times 2 is 72. Is that right? The trapezoidal sum, I don't have to actually write any of this out. What I do instead is I add up the right and the left and divide by 2. 44 plus 42, divide by 2. Obviously, it's going to be 43. Okay, I want to be clear that when we get to the AP exam, a little bit of this will change, and here's why. See how our difference stays constant every time? They will change it. And when they do, we can't just write 2 times everything. We have to calculate each rectangle manually. And then also our trapezoidal sum will change a little bit. But really, that's strictly just an AP idea. And that's partly why I don't really buy into some of the things the AP exam does. You'll never use it again, promise. But we'll get to that time being. For right now, this is what you'll be tested on come your test. You good with that? Okay, let's switch. Approximate the area bounded between the curve f of x equal to -x squared plus 16 on the x-axis, the y-axis, in quadrant 1. What's different about this example? There's no bounds, no cheat table. We'll make a cheat table, okay? How's that? What does the graph of -x squared plus 16 look like? Upside down parabola. Where does it cross the x-axis? Very good. -4 and +4 if you factor that and find the x-intercepts. It says that it is bounded between the curve, the x-axis, and the y-axis in the first quadrant. So we're only looking for that portion. 0 to 4. Very good. Jake said there's no table. Let's make ourselves a table. Okay? So I'm going to start with 0. What is the width of each rectangle? How many rectangles am I going to have? 5. If the width is 4 and I'm having 5 of them, then 4/5. So 0, then 4/5, then 8/5, then 12/5, 16/5, and 20/5, or 4. Are you okay with that? So the width is 4 over 5 times, and you plug them in. So f of, what do we plug in first? 4/5, right? Why? Right side. Then f of 8/5, then f of 12/5, 16/5, and then f of 4. So we could go to our table and generate those values. Can we skip that for the sake of time? But you all know how you do that, right? You just plug in the y equals, go to your table, generate the values, and then add them all up and multiply by 4/5. So how would the left hand of 5 change? I would have 4/5. Yeah, f of 0, very good. And what would be your last one? Good. Let's skip the midpoint for a second, go to trapezoidal. How would we then find the trapezoidal sum? Those two average together, so you would take R5, R sub 5 plus L sub 5 and divide by 2, and that would be your trapezoidal sum. But let's consider the midpoint. Does the width of the rectangle change? I still have 4/5. Yeah, I have to go in between. What's in between 0 and 4/5? 2/5. People make mistakes then when they go here. What? You went to what? Why'd you go 6/5? Yeah, you went between 4 and 8. But people, here's the mistake they'll make. They'll go up by 2/5 then every time. Because here you're going up by 4/5 every time. So they're like, oh, well, I go up by that number every time. No, you still have to increase by that 4/5, which will be the middle of this. So then f of 6/5, then f of, yep, 10/5, which is 2, then f of 14/5. Not used to my students reducing fractions so quickly. So here's what they do. They see, okay, so 4/5, 4/5, so I go up by 4/5 every time. So now they're like, oh, my first one's 2/5, so I'm going to go up by 2/5 to get 4/5, and then 6/5, then 8/5, and then 10/5. That's a common mistake. Please don't do that. Yeah. I don't care. I just want you to see the pattern that we're going up by 4/5 every time. That's why I wrote it out. So can we skip the actual calculation? Awesome. Then, example 3. Use the following graph to evaluate the sums over the interval 0 to 120. So what I'm going to do in this situation is I want 4 rectangles, and I do not have a table, and I do not have an equation. I have just this graph. That's not going to be that bad. What is the width of each rectangle? Yeah, I take 120 minus 0, and I divide by number of rectangles, which is 4, and I get 30. So 30 times. Where do I evaluate the first height? Then so it ends up being 30 times 240. Whoop. 7,200. So you can do the left-hand one on your own. Did you get 4,200? I did. I started at 0. Try the midpoint on your own. $5,700. And then how would you do the trapezoidal sum? Good. Excellent. Then what we can do is when we get back, we can do the last example, and I could give you your worksheet right now. How's that? Last example will take us a while, but I don't know if this one could be classified as a packet. Whoa, wait, we got 2 minutes yet. All right, allow this to be the example that bridges our learning from today to tomorrow. And tomorrow is super exciting. I already told you, right? Okay, tomorrow is for me one of the most, if not the most exciting lesson of the entire year. Tomorrow I will teach you how to add up the area of an infinite number of rectangles. Your brain will explode. You'll think it's awesome and exciting. It's really a good time. So, if you notice, I think the most that we've done so far is maybe say 12 rectangles. Well, let's, that's kind of for the faint of heart. Let's go to 100. Okay, let's go to 100. Now, in order to do 100, like problems 3 and 6 on your worksheet, you are going to use the assistance of your graphing calculator. Okay, because your graphing calculator can add up stuff quickly, and we're going to make this possible. So first of all, let's just get an idea. What does sine of x even look like? Okay, great. Looks like that. So, looks like a wave. Tell me something more about it. How about starts at 0? Period. 2 pi. All right. Here's a couple things that you don't know yet that are very important. First of all, when we find area, it's called integrate. And I told you that we're now in the study of integral calculus, and I'll bring up this idea of the integral tomorrow. But if we integrate or find the area from 0 to pi, we're going to come up with a positive result. It's kind of interesting, but if we integrated from pi to 0, we would be doing it technically backwards, and you would come up with a negative result. That's not really important right now, but in the future, if you don't go from the smaller number to the bigger number, if you go the other way around, it's going to be opposite in terms of value. Second piece is that when you look at area, area in mathematics can actually be positive or negative. Okay? Now, I know that that sounds weird, but is it possible to accumulate a positive amount of money? Is it possible to accumulate a negative amount of money? So therefore, in mathematics, area represents the accumulation of different pieces, and so that's why it can have negative value. Area above the x-axis, do you think is positive or negative? Below? So if you were wondering the area of the sine function, bounded between the function and the x-axis from 0 to 2 pi, what do you think it would be? 0. The positive and negative would cancel out, it's symmetrical, and you'd be done. But we're not wondering from 0 to 2 pi, we're wondering from 0 to pi. Okay? So I'm looking at just this portion right here. I want to divide it up into 100 rectangles. Awesome. So what is going to be the width of each rectangle? Pi over 100, right? The width divided by the number of rectangles. So it looks like I start here at 0, I end there at pi, and I'm going to have all these different spots that show me what the sub-intervals are. For example, this spot right here would be pi over 100, and then I would have 2 pi over 100. I know. And then 3 pi over 100, 4 pi over 100, so on and so forth. What would be just short of pi? 99 pi over, how about before that? Okay, and just, right. And so we see it's not to scale, but as long as I could draw the first few and the last few, that's going to be enough to really help me out. And here's how we add up the infinite number, or the 100 rectangles. We take the width, and we multiply it by the sum of the heights. Now, the width was no problem, was it? But adding up the heights, we're going to use an algorithm that I've kind of put together for your calculator, and it's going to help us out, make it a lot quicker. We multiply by sum. So that's a command that we're going to use in your calculator. And then we're going to create a sequence. Now, what we have to tell your calculator is, in order to determine the sequence that it adds up, is it wants to know how we calculate the height. What determines the height here? What do we use to determine height? Sine of x. So you type in the function, and then your calculator really needs to know the variable that it's using to plug stuff in, and it wants to use x. So you tell it to use x, and these are commas. You have a comma on your calculator we'll use, and then you need to tell it where to start. We need to tell its beginning spot. We need to tell it where to end, and we need to tell it how much to go up by between each interval, so the width. And we'll close with 2 parentheses. The sequent means, suppose my function was 3x, and I was going to start at 0 and end at 8, okay? And the width was 1, okay? Then your calculator says, okay, so it's 3x, and I'm going to start at 0 and end at 8, and the width is 1. Then I'm going to take 1 times 3, 2 times 3, 3 times 3, and I'm going to add all that up, okay? If you remember last year, we actually did a series, where a series meant you were adding it up. It's actually more of a series than it is a sequence, because you have that, well, the sum creates the series, okay? All right, so let's do this. Right-hand sum of 100. Let's write it out, and then we'll put it in our calculator. What is the width? Pi over 100 times the sum of the sequence. What's our function? Sine of x. Do you think I should work at radians or degrees? Radians. Then I do x. I'm doing the right-hand sum. Where is it? Where do I begin? Pi over 100. So this is what changes each time. It's your beginning and your end. If I'm doing the right hand, what's my end? Pi. And what's the width? So I want to enter that in my calculator. Instead of manually writing it out by hand, I can use my calculator technology in order to generate this sum. And I really do like this type of a problem because it requires us to use our technology and still understand those components. And we get a really accurate result. So here's how I get it. I go second, well first I got to go pi over 100. And then I go second catalog. Catalog is your 0 button. Can I move on? All right. Now we're going to press S for sum, but SU, so sum, is very close to T. So if I actually press T, you can see if I go up one, the sum value is right there. So that's going to be your quickest way to navigate to sum. Yeah. Okay, so you got a fancy-dancy smart calculator. I don't. And if you want to brag about that, that's fine. So, no, I'll show you how to then make it quicker. So I enter sum, and then I grab sequence. And that's going to be closer to the beginning of the S's. So I, again, go to catalog. I press S for sequence. And I scroll down to SEQ. And it's going to be the smaller case one. So catalog, S for sequence, and then scroll down. The lowercase one. You're crazy. And so now we enter our function, sine of x. Make sure you close that parenthesis. You're a funny-looking Q. All right. Comma, 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 comma. And then I have to type in x. So I'm telling it that that's the variable that we're going to insert these values for. What's the beginning value? Pi divided by 100, comma. End is pi, comma. Pi divided by 100, double parenthesis, booyah. It's going to take a while for it to think. It has to add up 100 numbers. It takes a while. And we're going to enter this to 6 decimal places, okay? Make sure that you're in radians, folks. So what do you think is this is an approximation. What do you think the actual answer is? Yeah, it is too. And I'll show you how to find the exact answer as well. We've done that once before, but we'll do it again. Now, let's do left hand. Can I show you how to save some time when you do left hand? Second entry. If you press second enter, it grabs the previous entry. So it just copied it. Now you can go into it and edit it. So all I want to change is instead of starting at pi over 100, I start at 0. And then my last one, d-wylen, is 99 pi over 100. Comma. And then my width is still pi over 100. Double parenthesis. Not the same. 1.99889. So you're right. It is pretty close, but it's important that you understand that we don't just want to write, oh, it's about 1.9. There are different values. I'll expect this written out correctly to 6 decimal places on the test. Oh, I'm sorry. I'm going to actually write this out for those watching. We did pi over 100 times the sum of the sequence of sine of x, and we started 0. We went to 99 pi over 100, and then our width was pi over 100. So that's what we did there. And now is the most challenging one, which is our midpoint sum. So I'm going to write it out. We still have pi over 100 times the sum of the sequence of sine of x, given the value x. But now this is a little bit more challenging. We need to find our starting point. Halfway between 0 and pi over 100. Pi over 200. Where do we stop? We stop halfway between 99 pi over 100 and pi. 199 pi over 200. So you would average them. So you take 99 pi over 100 plus 100 pi over 100, which is pi, and divide that by 2. And when you do, you get 199 pi over 200. So that's our ending. And then what was the width? Thank you for stating that, because that's what a lot of people will do on the test. The width does not change. People will write pi over 200. And you'll raise your hand on the test, like, Mr. Gens, like, I know I'm doing something wrong because I'm coming with like 0.5, and I know it's supposed to be close to the other two. But what am I doing incorrectly? I wish I could tell you, but now look at what you're doing. So let's try that. Are you doing 1,000? Oh. Jeez. Sounds fun. All right, so we start not at 0, but at pi divided by 200, comma, 199 pi divided by 200. Oh. It's pretty amazing your calculator is capable of doing this. I mean, some of your teachers, they're old enough actually remember when calculators could only add, subtract, multiply, and divide. So, no, I am not. When I was in college, when I was in high school, I had a TI-81. It was shortly after that the TI-83s came out, and that was pretty awesome. So, TI-81 could not do these type of algorithms and computations. It could not. So, it could graph and do some other neat options, but it could not do this. I don't know. I'll have to research that. But so anyway, it looks like the midpoint is between the two, isn't it? What do I do for trapezoidal? Yeah, 1.999836 plus 1.99889. I'm going to divide that by 2. 1.99836. I should teach my daughter how to do some of this stuff, and then she could like show her class, and they'd have a good time. Yep. I bet you didn't know we could do this. All right. Cool. So, if you want to check to see if your answers are reasonable, just go ahead and enter the sign function, and then do second calculate. Which one do we calculate? 7. That's our new calculate option. And so you can see that my window isn't very good here. If I change my window a little bit, say a -2 to 2, and if I change my y value to, no, that's opposite. So like -4 to 4, and then -4 to 4, I'm sorry, and then -2 to 2. Okay, now I got a much better graph to look at, and I want to calculate that area, and my lower limit is 0, and my upper limit is pi, and it draws all my rectangles, and boom, 2. Well, remember, this is an approximation with 100 rectangles, but it's pretty good, okay? And that's that. So please make sure that you're, again, problems 3 and 6, you're going to use your calculator option for that. Make sure that you reference this formula that we wrote down at the top. You're going to use that. You're going to use that on the test as well. Okay. All right, big day tomorrow. Get some sleep. Got to be ready. Infinite number tomorrow. Tomorrow we do R sub infinity. Okay. You're right. It's not a number. You got the question right. Good job, Jake. You listened to my song earlier this year. I'm so proud of you.